Welcome, everyone. For today's prep, we're going to see how to find the intervals of concavity given the formula for a function. So we're going to see how we can use the second derivative to help us find where our original function is concave up, where it's concave down, and then we'll also see how to locate the inflection points, so the places where our graph changes concavity. All right, so let's start with our main result here that we're going to be using. And what this result tells us is how the second derivative relates to the concavity of the original function. So let's suppose that we're looking at an interval of our x-axis. So we have this open interval from a to b. And we know on this interval that the second derivative is greater than 0 for that entire interval. So we know that the second derivative is positive. Well, then we can conclude the original function f is concave up on that interval. So it has this kind of shape to it. Now, if our second derivative is less than 0, so if it's negative, well, then we can conclude the opposite. The original function f is concave down. So it has this kind of shape. So our strategy here is we're going to be looking for where f double prime is positive. And if that's the case, then we'll be able to conclude, careful, I write that, that f is concave up. And if f double prime is negative, we'll be able to conclude that the original function is concave down. So, again, we're going to be investigating some function f, and we're going to be using its second derivative to help us with that. All right, so how are we going to do this? So the first step in our strategy here, well, we got to calculate the second derivative. So we got to calculate f double prime. Then we want to find what are called the inflection numbers of f. So this, another fancy name, but this is similar to what we did with the first derivative and the intervals of increase-decrease. So the inflection numbers for some function f are the places where the second derivative is either 0 or the second derivative is undefined. So just like when we were doing the intervals of increase-decrease, we located where the first derivative is 0 and where the first derivative is undefined. Well, now we're doing this with the second derivative. So when we talk about these inflection numbers, you want to kind of keep in mind what we did with critical numbers. Critical numbers involve the first derivative. Inflection numbers involve the second derivative. So what did we look at for critical numbers? Well, we wanted to know where f prime was equal to 0 or where f prime did not exist. So we're going to be doing the same thing, but now we're going to be involving the second derivative instead. Now there is one extra kind of requirement here for it to be an inflection number, and that is f double prime has to switch signs. So it's a little something extra. And really why we need this is so that we get a change in concavity. So that's what this f double prime switching signs means. This is going to give us a change in concavity. All right, so we're still going to be interested, though, places where the second derivative is 0 are undefined. So that's step 2. We're going to create our sign, or find the inflection numbers for f. So look for where the second derivative is 0 undefined. And then we're going to do a sign chart for f double prime. And then from that sign chart, we'll be able to get the intervals of concavity. So these first 4 steps, these are how we're going to find our intervals. And these should feel very similar to our strategy for finding the intervals of increase-decrease, except in that case, we use the first derivative. So we'd calculate the first derivative, we'd figure out where the first derivative is either 0 or undefined, we would do a sign chart for our first derivative, And then from that sign chart, we'd be able to get the intervals. So the work here is going to be very, very similar to our intervals of increase, decrease, except now we're just going to be using the second derivative. All right, so from here, we want to then locate our inflection points. So we want to, those inflection numbers that we found, we just want to check that they're actually in the domain of our original function, so that there's actually a point there, and that we actually do have a change in concavity. So we're really looking for this F double prime switch in signs kind of thing. So if that's the case, well then we actually do have an inflection point there, and so then we can find the y coordinate. So we'll come back and talk about this strategy, but let's try an example. So we'll start with just a nice polynomial here. So we're going to do it all. We're going to find the intervals of concavity, and we're going to find the inflection points for this function. So our function here, 1/3 x cubed minus 2x squared plus 3x plus 1. And I think this is the same function we used when we did an interval of increase decrease example. So we're going to now get the intervals of concavity for this thing. All right, so what's the first step? First step, we got to calculate second derivative. And once we have the second derivative, usually it's going to be helpful to factor it. We'll see though. This one might be an easy enough second derivative where we actually don't have to factor. But sometimes if you need to, it's a good idea to try to factor. So, all right, we want to calculate f double prime. So, well, to do that, we need our first derivative. We need f prime. So let's get f prime. Derivative of that first term is going to be x squared. Derivative of the second term is minus 4x. Derivative of the third term is plus 3. And then derivative of that plus 1 is 0. All right, so that's our first derivative. Well, we need our second derivative, so we do it again. So we'll call this f double prime. And this is, if we differentiate, derivative of that first term is 2x minus 3. And then derivative of the second term is minus 4. So, no, not 2x minus 3. What did I say? Derivative of that first term is just 2x. Derivative of the second term is minus 4. And then the derivative of that 3 is just 0. So we end up with our second derivative being this 2x minus 4. And if we wanted to, we could factor this. So this one does factor, but it's simple enough where when we get ready to actually find our inflection numbers, we're just going to be able to solve this. So let's get our inflection numbers. All right, so what are the inflection numbers? Well, there's two ways we can get one. It's where our second derivative is either equal to 0 or where the second derivative does not exist. All right, so how can a function like this have a place where it doesn't exist? Well, really, we'd be looking for division. So we'd be looking for division by 0. And in this case, there's no fractions, there's no negative exponents, so there's no division by 0 here. So, in this case, we're not going to get an inflection number this way. So our second derivative here is always defined. So again, you're just kind of looking for division by 0. All right, so, but we are going to get something from our second derivative setting it equal to 0 and solving for x. So let's set it equal. That'll give us the equation 2x minus 4 equal to 0. And then we can add 4 to both sides and then divide by 2. So when we do that, we get x is equal to 4 over 2. And if we simplify, x is equal to 2. So this is one of our inflection numbers. All right, so now we want to do our sign chart. So that's the next step. So we're going to do a sign chart for f double prime. So just like we did with our sign charts for f prime, we're going to start by drawing the x-axis. And we're going to plot all of our inflection numbers that we found. So x equals 2 in this case. And what that x equals 2 does is it slices up our x-axis into, in this case, into just two parts. Minus infinity to 2, and then 2 to infinity. And our goal here is to figure out what is the sign of f double prime, and that'll tell us ultimately what f is doing. Now, if our second derivative had more factors here, we would kind of include more rows here just to help us out. So we'd go through and find the sign for each of the factors. But because it's just this 2x minus 4, this is a simple enough function. We're just going to plug our test numbers in right into this and see if we get something that's either positive or negative. All right, so let's start with our first interval. We just want some test number to be less than 2. So 0 is always a good one. And if we plug 0 into our second derivative, the 2x minus 4 here, let's see what we get. We get 2 times 0 minus 4, which is negative 4. All right, so that tells us on that first interval, f double prime is negative. So then we go on to our next interval, 2 to infinity. Pick a number bigger than 2. So 3 is always a perfectly fine test number in this case. Plug it into the second derivative and see what you get. So we get 2 times 3 minus 4, which is positive 2. All right. So that tells us f double prime is positive over here. And finally, now we know when f double prime is negative, our original function is concave down. So f is going to be concave down on that first interval. And when f double prime is positive, that tells us our original function is going to be concave up. All right, so we've got our intervals at this point. So now we can just kind of summarize our intervals of concavity. So what we found is that the original function f is concave up on the interval 2 to infinity. And the original function f is concave down on that other interval, minus infinity to 2. All right, so we've found our intervals of concavity here. Now we want to look for the inflection points. So we got our intervals of concavity. We want to look for any inflection points. So the x values that we found in step 2, these are really the possible places where we might have an inflection point. We just got to check one extra thing. So we might have an inflection point here. We got to check one extra thing. Well, actually, two extra things. So this x value has to be in the domain of our function, and we'll kind of figure that out along the way. The main thing here, though, is that we need to see a change in concavity. So if we go to that x value on our sign chart here, x equals 2, what we see is that on the left side of x equals 2, our original function's concave down, and then when we get to the other side of x equals 2 on the right there, our function switches and is now concave up. So what we see here is that there is a change in concavity. So this is really step 5. You want to look, if you're going to find the inflection points, you just got to verify, is there actually a change in concavity at that point? And in this case, yeah, we're going from concave down on one side to concave up on the other side. So you want to look for a change in concavity. So check. We did see that. So now we just want to get the last part of this, the inflection point. When we write down the inflection point, if the directions say find the inflection point, it means find the x-coordinate and the y-coordinate. So right now, we only have the x-coordinate. We want to also get the y-coordinate. So that's the last part of this. Get the y-coordinate. So how are we going to get the y-coordinate for our point? Well, we'll take the x value that we found and just plug it into the original function. So the x-coordinate we found was 2, and we're going to plug this in to the original function and see what we get. So just to be careful here, we're using the original. Got a lot of other functions floating around when we do these problems. So there's the first derivative we calculated, there's the second derivative we calculated, but when we're trying to get the y-coordinate, we're trying to get the y-coordinate for our function. So we want to use our original function here. All right, so let's plug 2 back in. Again, we're not going to use the first derivative to get the y-coordinate. We're not going to use the second derivative to get the y-coordinate. We're going back to the source to get our y-coordinate. So we're going to plug 2 in up here. And when we do that, we get 8 over 3 minus 8 plus 6 plus 1. And that simplifies to what? We get negative 8 plus 7, so negative 1. And that simplifies to 5 over 3. So we get 8 over 3 minus 8 plus 6 plus 1, which simplifies to just 5 over 3. So now, my 5s. There we go. So now we just put it together and write down the coordinates of our point. So we have an inflection point at 2, 5 over 3. So our answers here, we've got our intervals of concavity nicely written out, and we've got our inflection point. And just be careful when we're doing these. The interval of concavity, these intervals of concavity, these are kind of slices or sections of the x-axis. And the notation kind of looks similar to our point notation, where we have parentheses on either side. But for a point, this is more a specific place on the xy plane. So this is an x-coordinate and a y-coordinate. So we've got our x-coordinate that we plugged in, and then the y-coordinate that we found. So just a slight different thing to note there. Inflection points are kind of a specific point on the graph, whereas these intervals of concavity, these are slices of the x-axis. All right, so we'll try some more of these examples in class. So we'll see you then. Bye-bye.